Okay, so one day I wanted to have some protein milk and I needed to mix it with a mixer because if you don't mix it, the protein powder creates lumps inside the milk and I don't like that. While I was mixing it, thought to myself, I also want this milk to be a little bit warm. And I was thinking about the process of taking the heating pot, turning on the stove, taking a glass, putting the milk on the stove, etc., etc. And I was feeling very lazy. So my ADHD brain came out with a question. If I just kept mixing with the mixer, will the mixer itself heat up the milk, and how much time would it take for the mixer to heat it up? And for this, today we are going to answer with modeling and simulation and with physics. So let's get right into it. So we have a milk heater simulator, and the mixer performs mechanical work to the milk that turns into heat through viscous friction. And the main equation is that the heat transfer to the milk is going to be equal to the power times time, and the difference in temperature in time is going to be equal to the power transfer, the heat transfer to the milk times the mass times the specific heat. The main idea is that not all the power is going to go to the milk for heating. Some of it will dissipate into the motor of the mixer and noise, etc. So this is a this is a coefficient that we don't know actually, but let's start with the main initial conditions, which are the temperature of the room is going to be 20 degrees. We are going to consider the initial state of the milk equal to the temperature of the room, even though maybe it's not true, because if I take the milk from the fridge, then it's going to be slightly colder. Then we are going to consider the time step equal to 0.1. Then we are going to consider the initial time equal to 0. And for now, let's say that the end time is going to be 600 seconds. That is going to be around 10 minutes. And we are going to have some constants, some, let's call them parameters, that are some physical constants that we are going to need, including the power of the mixer. We are going to consider 150 watts because it's a small mixer. Eta is the efficiency coefficient, and we are going to consider it 10%. Let's say that only 10% of the power is going to be the power that gets transformed into heat. Then we are going to consider the volume of the milk in milliliters. And it's going to be 200. Then we are going to consider that the mass of the milk is going to be the volume times the density of the milk divided by 1000, so we can get the mass in kilogram. And finally, we can say that the specific heat is going to be 3930. We are going to start with defining the derivative, which is the main equation to solve, which will return, as we explained in here, will return the power, okay, but it's going to be the power effective, which is going to be power times eta. So power effective divided by mass times specific heat. And we are going to solve this with a loop. It's a basic Euler integration. And with a while loop, we are going to say that while time is smaller than the end time, the state of the milk is going to be equal to the derivative of the state times the difference in time. And then we are going to increase time. So that's it. And we are going to check how much did the milk heat up in this period of time. So we are going to check now how much did the milk heat up with these conditions in 10 minutes, and it is, the temperature is equal to 31.12 degrees. So it heat up in 10 minutes around 10 degrees Celsius. Not bad. The only thing is that this model is only increasing, so it only goes up. And that is not real, because the milk also loses heat to the room. So we are going to need to introduce some coefficient that helps the milk to lose some heat to the room. We are going to apply the Newton's law of cooling. And let's say that the milk has a K coefficient of cooling equal to 1.5, because the milk becomes hotter, so it dissipates heat to the room. We are going to consider the, let's say, heating is going to be equal to P effective, and cooling is going to be equal to K times the difference in temperature. And then these derivatives should turn heating minus cooling divided by the mass times the specific heat. And now we can go and check this out. And as we can see, with these coefficients, the milk warms out very slowly, way more slower than what we thought. Now there's a tug of war that the mixer adds heat and the room takes it away. But eventually they will balance and the milk settles at an equilibrium temperature. And we can actually compute that equilibrium temperature using simple physics, and we can consider that the temperature of equilibrium is going to be equal to the temperature of the room plus the effective power divided by K. And here we are going to have a check, because let's say that the equilibrium temperature is at a certain point, then the milk doesn't heat up more than that. But the main question for me is if I wanted to heat up the milk to a fixed temperature. Let's say that the T target is going to be equal to 50 degrees Celsius, okay? The target temperature. And I want to heat up the milk until this temperature. Now, this is why I need the equilibrium temperature, because if the equilibrium temperature is smaller than the T target, then the milk is going to heat up until that point and it will not heat up anymore. So here we need a check. And then we are going to consider that else, and we print this. So yeah, we can try this out. There it is. It says that the equilibrium temperature is 30 degrees Celsius, so it will not heat up until 50 degrees. But if I change up the power of the mixer, what will happen? Well, the equilibrium temperature increased, but still not that easy to reach up that temperature that we needed. Let's say that eta is going to be 15%. What will happen? Well, it still increases 45 degrees.